Okay, today we're talking about scientific notation. One thing that you guys need to understand about chemistry is that everything that we do kind of builds on itself. So if we do something and you don't understand it, like last week when we did significant figures and you didn't, if you had issues with it, or if you don't remember it that well, you might want to go back and rewatch that video or go back and do a couple more example problems or anything like that just to kind of cement it in your brain, because this stuff that we're doing today builds off of that. All right. So with that said, let's go ahead and get started. And you guys will have to just bear with me and ignore the dog in the background. He's mad because I put him in his crate. All right. But here we have scientific notation. So the general idea here is that sometimes when we're working in chemistry, we're working with very, very large numbers or very, very small numbers. And having to write those out every single time we use them can get to be a pain in the butt and just really difficult to actually do math problems with and kind of understand the scope of them just at a glance. So what we do instead is we use scientific notation. And what that looks like I'll give you all an example of a number that you guys will see a lot later on in the year. This is called Avogadro's number. And it's the number of atoms that are in a mole of a substance. And y'all won't have any idea what that means yet, but we'll get to it eventually, I promise. And what this would look like if we had to write it all out, this is the scientific notation version of it, the shortened version. If we wrote this out as a regular number, it would look like this. All right, with the 6022 and then 20 zeros on the end. So you can imagine how writing that out every single time you had to use it in a math problem or something could get annoying and frustrating. So that's where scientific notation comes in. Now, there's a couple of rules to when and how we can use it. Wait on the puppy. Okay, there's a couple of rules to when and how we can use this. And the first one is why I was saying you want to go back and make sure you understand significant figures from the other day. When we are writing out scientific notation, you only write as many digits in your little base number as there are significant figures in the original number. So here, when we did the 6.022, the reason we stopped after those two twos and didn't, include any of these long string of zeros is because none of these zeros are significant figures, right? If we go back and think of our sig fig rules, we know that the 6, the 2, and the 2 are all significant because they're non-zero digits. And this 0 right here in the middle is significant because it's stuck in between two significant figures, the 6 and the 2 there. But none of these other ones are significant figures. When we write out the scientific notation, we just write these first 4 digits and then abbreviate it with the times 10 to whatever power. All right, so these examples on the PowerPoint, the 603 million, if you look at it, the 6 and the 3 are both significant figures, and the 0 between them is significant because it is sandwiched between them. So in that one, we have 3 significant figures. So we would write it as 6.03 to get those 3 sig figs in, and then do the power. And the bottom one, the only sig fig in 40,000 is the 4. So when we wrote that out, we would just have the one significant figure and then the power. And we'll talk about how you determine what the power is later. But for now, you got to know that you're only using as many digits as there are sig figs in the original number. All right? The second rule is that the base number, which is what we call this number out in front of the 10 and the power, the first thing you write, it's called your base number. It needs to be between 1 and 10, meaning that it has one digit to the left of the decimal point. All right, so technically, this 12.9 times 10 to the 10th or 0.129 times 10 to the 12th would be the same value as the correct scientific notation. But in order for it to be correct scientific notation, the base number has to be between 1 and 10. So that's how you're going to write it. Alright, the third rule is that the exponent in the power of 10, so this little number here, the times 10 to whatever power, the way you determine that, it's equal to the number of spaces you have to move the decimal point. So if we go back and look at our original example from the last slide, the 1, 2, 9, 0, 0, 0, 0, 0, 0, 0, 0, 0. Alright, and we know that first step is to figure out how many sig figs we have. So the 1, the 2, and the 9 are all significant, and none of these zeros matter because they're not sandwiched between anything, and they're not after a decimal or after another sig fig or anything like that. So we have 3 significant figures, the 1, the 2, and the 9. And our second rule says that the base number needs to be between 1 and 10. So like we talked about a second ago, our base number is going to be 1.29. Alright, and then all scientific notation is going to be times 10 to the power of something. And that something is what you determine by figuring out how many places you have to move the decimal. So originally, in our big number, the decimal point is all the way here at the end. And when we've written it, it's all the way over here between the 1 and the 2. So how many spots are between here and here is what we need to count to figure out what our power is going to be. So if we start here and we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, we're back to the original spot, and we know that it is to the 11th power. Alright, and that'll make more sense when you guys see a couple more examples. Alright, and then the fourth rule determines which way you move when you are counting those jumps to get the right power number. Alright, a positive exponent on the 10, so like we just had, this is a positive 11, means it's going to be a large number. So this 129, what is this? 129 billion. I'd say that's a pretty large number. Alright, and a negative exponent means it's going to be a decimal number, a small number. So if we look at these examples here, we've got 4.19 times 10 to the 6. And if we're going to convert that back to original standard notation, we know that we need to move the decimal point 6 places because of it's to the power of 6. So we can say 4, 1, 9, and the decimal point was originally here, so we go 1, 2, 3, we can put a 0 there, 4, 5, and 6. We end up with 4,190,000 with the decimal point here at the end. And if it was 4.19 times 10 to the negative 6, we move the decimal point the other direction. So this time, if we start here with our decimal point, it moves here to in front of the 4, then there, and there's room for another 0. That's 2 jumps, 3 jumps, 4 jumps, 5 jumps, and 6 jumps. Sorry, I kind of ran out of room there, but you guys get the idea. So now, instead of being 4 million, it is 0.00000419. Alright, so the exponent being positive or negative determines which direction you move when you are counting your decimal places out. Alright, so here we've got some examples. So we're going to convert all of these into scientific notation, or if they're already in scientific notation, we're going to convert them back to standard notation. So here, our first example, 347,000 If we go back and look at our rules, rule 1 is we are only writing out as many digits as there are sig figs in the original number. So back to our example, we got to count up our sig figs. The 3, the 4, and the 7 are all significant figures. Those 3 zeros behind them are not. So when we write this out as scientific notation, we're going to have our 3, our 4, and our 7 as part of it. Rule 2 says that the base number has to be between 1 and 10. So looking at these 3 significant figures that we have, the spot to put our decimal to make it between 1 and 10 is right here after the 3. Alright, and then all scientific notation ends with the times 10 to a certain power. We just need to figure out what that power is. So if we come back to our original number and look and say, this is where we decided to put our decimal, how many jumps do we need to make to get back to where the decimal was originally? We can count them up. Go 1, 2, 3, 4, 5. So it's times 10 to the 5. And then the last thing is determining whether it is a positive 5 or a negative 5 for our power. And this is a large number, 347,000. It's larger than 1. So this is going to be a positive 5 here in the exponent. All right, let's try another example here. We've got 902 million, and we are trying to convert that into scientific notation. Again, first step, figure out how many sig figs you have and write them out. So here we've got our 9 and our 2 are significant because they're non-zero digits. And then the 0 in between them is significant because it's sandwiched in between the 2 significant figures. None of these other zeros after count as significant figures. So we're just left with 9, 0, and 2. Again, it needs to be between 1 and 10 for our base number. The only way to do that is to put our decimal point right there after the 9. And we know it's going to be times 10 to the something power. We just have to figure out what that power is going to be in order to move our decimal from where we put it to where it actually should be back here at the end of the number. So we count our jumps. 1, 2, 3, 4, 5, 6, 7, 8. And we get 9.02 times 10 to the 8th power. Alright, and to determine whether there should be a positive or a negative power, we just look and see, did we move our decimal to the right to make this number bigger? That means it's going to be a positive. And if we move it to the left to make this number smaller, make it a decimal, that means it should be negative. So in this case, we moved it to the right when we were doing our jumps. So this is a positive 8. All right, one more example going this way, and then we'll do those other two going from scientific back to standard. So in this case, we've got 0.00, let me make sure I get the right number of zeros here, 0.00658. All right, and we want to turn it into scientific notation. So here, we're going to go ahead and go count our significant figures as our first step, same as we've been doing. We've got these 3 are all non-zero digits. And then if we look at these other zeros here, there's no zero out in front, there's no significant figure out in front to sandwich them in there or to make these decimal ones come after a sig fig. So none of them count. So it's only the 6, the 5, and the 8. And then in order to put our decimal spot in the right place, it has to be between 1 and 10, so it's got to go right here after the 6. So we're putting it in right here. Now this one, see these other two, when we moved from where we put it to where it should be, we were jumping to the right. On this one, we've got to go back to the left. So we count them up. This is times 10 to the something power. We count them up. We go 1, 2, 3, 4, 5. But this time, since we were moving back to the left and making our numbers smaller as we went, it is a negative 5. So here our final answer would be 6.58 times 10 to the negative 5. All right, we've got two more. So here, these last two are showing you going from scientific notation back to standard. So here, we start off with 2.14, so we know we have 2, 1, and 4 as the significant figures in our original number, and we need to figure out how many zeros we need to add on at the end to make this correct, right? If we have our decimal point starting right here between the 2 and the 1, and we know this is 14, the power, so it's going to make 14 jumps to the right because it's a positive number, we're going to just start counting. 1, 2, 3, that's 1 0, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 jumps. So this is 2, 1, 4, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros on the end. Would be your number in standard notation. All right, our very last one, 5.3 times 10 to the negative 3. All right, so on this one, we've got 5 and 3 as our two significant figures. We know the decimal point is originally here, and we've got to move it back to the left this time because our exponent up here at the top is a negative exponent. So remember, positive exponent means you're moving to the right, making the number bigger. Negative exponent means you're moving your decimal place to the left, making your number smaller. So here, we're going to jump 1 to get back out in front of the 5. Another 1, a 0 goes there, and then another 1 for another 0, and our decimal point ends up out in front of that. So your final answer here on this one would be 0.0053. Alright, so that is converting between scientific and standard notation. The other thing we're going to talk about today is multiplying and dividing with scientific notation. We're not going to worry about adding and subtracting because you won't be asked to do that very often, and because a lot of the times adding and subtracting things with high exponent numbers like that doesn't make much of a difference because one of them could be orders of magnitude smaller than the other one. So multiplying and dividing is the important thing that we're going to worry about. So when we are multiplying and dividing scientific notation, you worry about the two base numbers first, and then you deal with the exponents second. So when you're multiplying the two base numbers, you just multiply them or divide them together like they were regular old numbers. And then when you deal with the exponents, when you are multiplying them, you add the two exponents together, and for division, you're going to subtract. All right, so let me show you what that's going to look like. If we've got here 1.36 times 10 to the 4th, and we are multiplying that by 4.9 times 10 to the 7th. So like we said earlier on the previous slide, you multiply or divide the two base numbers first. So the 1.36 and the 4.9, we're going to multiply them together to start off with. So we'll just go over here to my calculator. I'm going to say 1.36 times 4.9 is equal to 6.664. All right, and then like it says here on this previous slide. For multiplication, we're going to add the exponents. So what that means is these powers, the exponents on our times 10 to the whatever, you add them together. So here we've got 4 and 7. So 4 plus 7 equals 11. So this is going to end up being times 10 to the 11th. Does that make sense? I don't know why I asked a question because y'all can't answer me. But that's how it's going to work. Remember, one thing though, when we talked about multiplying and dividing with significant figures, you can't have more significant figures than you had when you started, right? When you're multiplying and dividing, you have to round down to the least precise value of significant figures in your two original terms. So if we're looking here at 1.36 and 4.9, the 4.9 has fewer significant figures. It has 2 to this one's 3. So we need to round our answer to only have 2 significant figures. So that would be 6.6, and then we look at the one after it to determine whether we round up or not, and this is higher than 5. So we end up with an answer of 6.7 after we round up times 10 to the 11th. And this would be your correct answer with the right number of significant figures. All right, one more. So here, this is division. So we've got 8.6 times 10 to the second power, and we are dividing by 7.23 times 10 to the sixth power. So here, just like in the first one, you deal with the base numbers first. You divide 8.6 by 7.23 and see what it gives you. So here we're going to go back to my calculator. 8.6 divided by 7.23, and you get 1.18948, blah, 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 blah. Whole lot of sig figs there. But remember, we only care about as many sig figs as our least precise original term. So this 8.6 has 2 significant figures. So, oops. Hold still. In our answer, we only care about 2 significant figures. So 1.1, and then we decide whether we round up or leave it like that based off of the next decimal place. So the 1.18 should round up to 1.2 times 10 to the something. We don't know yet. All right, the rule for division, if we go back a slide, is that when we are dividing, you subtract your exponents. So remember, you got to do it in the right order. So the one you are dividing subtracted by the one you're dividing by. All right. So the first one minus the second one. So here you're going to have 2 minus 6, which comes out as -4. All right. So your power here is -4. So this would be your answer for the second example there. Okay, let's go look at your homework real quick and do one example out of there. So here I'm in Canvas. This is your scientific notation notes page. The video will be on here. Obviously it's not yet, but you've also got your PowerPoint, and you can download the PowerPoint if you want to have a copy for yourself. All right, and then we're looking at your homework here. So if we click preview, these first two, converting from scientific to standard notation, pretty straightforward. I wanted to show y'all an example. Here we go. So when you are converting from standard notation to scientific notation, the way I've set this up is you have one box here to put your base number in, and one box here to put the exponent in. All right, the times 10 has already been taken care of. So all you got to put in is the base number and the exponent. That way you guys know how you're supposed to format it. So I'll give y'all a freebie on question 8. we'll do that one as an example. So we've got 4, 2, 3, and then 4 zeros, 0, 0, 0, 0. And we're trying to convert that to scientific notation. So we're going to look and say our sig figs here are the 4, the 2, and the 3. And these zeros are not significant. So it'll be 4.23 times 10 to the something power. And we need to figure out what that power is. That'll make us move our decimal point from where we've put it here after the 4 to where it originally was. So that's 1 jump, 2, 3, 4, 5, 6. So it's times 10 to the 6. So when you put that in, it should look like 4.23 times 10 to the 6th power. All right, the rest of these are up to y'all. If you have questions about them, you get stuck, let me know and I'll help you out. If you're an online student, just email me, or Tuesday and Wednesday afternoons, I'll be after school. We can Zoom and figure it out if you need more help. All right, good luck.